So let's look at the definition of polynomial on page 3. An expression formed by adding a finite number of unliked terms is called a polynomial. Well, that's kind of annoying. What's a term? If we back up a little bit, a term, a constant or a variable or a product of a constant and a variable is called a term. For example, 2x or negative 3x squared are all terms. So a polynomial is made up of one or more terms. And it says finite, meaning it can't go on forever. There are infinite polynomials. We obviously can't write them down because they're too long. But we just write as many as we need and then we stop. You know, like 10 million terms or something like that. We obviously won't do that in this class. So the variables can only be raised to a positive integer exponent, which is a really fancy way to say whole numbers. So a polynomial is a list of variables and numbers where the exponents are all whole numbers. No fractions, no negatives, no square roots on the variables. You can have square roots on the numbers, but the exponents on variables have to be whole numbers, and that's the only rule. But that rules out a whole bunch of things. There are no square roots of variables, no fractional powers, no variables in the denominator of any fractions. Okay? So if we look at this assignment, which expressions below are polynomials? Let's throw out the non-polynomials to begin with. Which ones are not polynomials? Three is not. How come? It has a variable in the exponent. That's a problem. Not a polynomial. What else? 4 is not. Why is 4 not a polynomial? Variable in the denominator. Is it okay to have a number in the denominator? Yes. In fact, we can ignore all of the numbers in there. If we just look at the variables, that will determine whether or not it's a polynomial. So number 1 is. Okay. What else? 2 is not. Why is 2 not a polynomial? I have some negative exponents. What if it was 5 to the negative 2? Would that be a polynomial? Yes, because the numbers don't affect it. It's just the exponents on the variables. All right? Number 5. 5 is a yes. Number 6. No. It has a polynomial in the denominator, but the expression itself is not because there are variables in the denominator. Number 7. Yes. Number 8. No. It has a 3/4 exponent on a variable. So 8 is a no. Okay. Right. Only whole numbers. 0, 1, 2, 3, 4, and on up. And in the book they said positive, what did they say? Non-negative integers. Let's look at that again. Raised to positive integer exponents. Well, you can actually have a 0. If I had x squared plus 2x to the first minus 6x to the 0, what is x to the 0? 1, so it's really just minus 6. So the book doesn't give a very good definition. It should have just said whole numbers. Well, in its case, it should have just said natural numbers. But actually, whole numbers is true because if you raise anything to a 0, it's just 1. And that's still a polynomial. So we have a polynomial, and I've made a mistake. Change the plus 3 to a minus 3. So they're all supposed to be minus 3s. I didn't look closely enough, apparently, when I wrote this. So we have a polynomial expressed in 4 ways. It's the same polynomial in all 4 versions. The only difference is sort of what it means. The first one, what do we call a polynomial without an equal sign? I'll give you a hint. Look at the directions to the first problem. It's called an expression. So that's an expression. Number 12, you know the name of. F of x equals, that says that it's a function. So number 12 is a function. What is a function? You remember the definition of function from last year? It's slipped your mind. Yeah, it passes the vertical line test. Okay, that's one way to look at it. The definition says a function has one output for every input. So for every x, there is one y, which means it passes the vertical line test. Because every time you draw a vertical line, it only hits the graph one time. Well, this is in function form. If I wanted to graph a function, what do I need to do? I need to set it equal to y. So I can turn number 12 into number 10 by replacing f of x with y. I haven't changed the polynomial, I've just changed its form. And this can be represented by graphing a curve. So let's do that. Everybody pull out your calculator. We're going to graph x squared. Oh, that's annoying. X squared minus 3x minus 3. So y equals, this polynomial is the entire graph. What happens if I throw out the y and replace it with a 0? That narrows the entire graph down to a set of numbers, a small, in this case, 2 numbers. So this is a representation of the roots. There are an infinite number of y's in this graph. Everything from somewhere near, what is that, -5 and up. All y values from the bottom of that parabola up are valid. They're part of the range. But if I take all of those y's and I throw them out and I keep only the zeros, that is saying, where does the graph touch the x-axis? Because on a graph, this line is the line y equals 1. This line is the line y equals 2. What line is right here? Y equals 0. So where does y equals 0 touch the graph of x squared minus 3x minus 3? At the roots, here and here. Now in this case, it looks somewhere close to -1 and somewhere close to +4, but it's not very perfect. It's certainly not whole numbers, or integers, I guess. But that's the difference. This is a function, meaning it follows the rules of functions. This is a graph, and if we shorten that graph to include only y equals 0, then we're looking for the roots. Anybody remember how to find the roots using your calculator? Second trace. Don't do trace. It'll be close but not accurate. Second trace. We want to find the zeros. Roots have 3 names. They're called roots, they're called zeros, and sometimes they're called solutions. So I push number 2, and it's going to ask me left bound. What does that mean? So if I have my graph here, and it wants my left bound, it's asking you to pick some x value to the left of the root you're trying to find. It doesn't matter what root you find first. So if we focus in on the left root, I want to pick some number to the left of that root. So the root appears to be -1, so I'm going to type in -3. And you'll see that little arrow at the top pointing to the right. Now it says right bound. What is a number to the right of that root? 0 would work. Why would it be a bad idea to pick 6? Because that would include the other root. And the goal is to isolate the two roots. It would be nice if you could just go to the root and hit enter and say find that, but the calculator wants more information than that. So here is my left bound. Now it asks for right bound, and I'm going to put 0. So I plug in 0. And you can see those arrows, and my root lies between those two arrows, which is good. And now it says guess. So for my guess, I'm going to guess -1, and the root is -7.9. So one of my answers would be -0.79. And then I do the same thing for the other root. Second calc, 0. What would a good left bound be? 2 would work. So 2 is somewhere to the left of the root. Okay. A right bound? 5 or 6, doesn't matter. And for my guess, I'm going to put 4. And my answer is 3.79. Now, does the polynomial need to be in 0 equal form to find the root? It doesn't matter. If you have a polynomial, it doesn't matter what form it's in. If I say find the roots, then you're asked to find the roots. However, if you see a polynomial in this form, that means find the roots without any instructions at all. If you have a polynomial that equals 0, that is enough to solve for the roots without any instruction. So if you look at numbers 13 through 18, those polynomials are in several different forms. But the instructions are the same. Use a graphing calculator to determine the zeros. I also want you to use those zeros to create the factors, just for practice. So for the first one, I'm going to type in 4x minus 32. Oh, sorry. 4x minus 32. That's not a quadratic. Can it still have roots? Yeah, any graph that touches the x-axis has roots, and even some that don't touch. What are the roots there? Just 8. How come it only has one root? It's a linear equation. It has an x to the first. It's a first degree polynomial, so it can only have as many as one root. All right? So what is the factor associated with x equals 8? Remember yesterday we took a polynomial? Close. We took a polynomial, turned it into factors, and then turned it into roots. X minus 8. There we go. What happens if you graph a quadratic and it doesn't touch the x-axis? It has imaginary roots, which cannot be determined by the calculator, at least not in an easy way. If you played around with it enough, you might be able to figure it out, but it would be not worth your time. So number 14, x squared minus 6x minus 27. And just so you know, all of the answers on this worksheet are whole numbers except one of them. So you don't need to do second calc 0 until you find the one that doesn't actually touch a nice number. Okay, so zoom, push zoom 6, and you change your screen back to something else. So if you happen to be zoomed in somewhere, so I don't see anything, my window is wrong. So if I push zoom, there are a whole bunch of different options, but zoom 6 is the standard window, and that will take me to the 10, 10, 10 window. And there are some problems that you'll graph and you won't see the answer. So you'll need to change your window. You can zoom out. The trouble with zooming out is you don't actually see the tick marks very well. But if you push window, your x goes from -10 to 10, and your y goes from -10 to 10. If you change those numbers, then you'll change your graph. And if you ever want to get back to normal, just push zoom 6, and that will take you to the standard window. So my roots are x equals -3 and 9. What would the factors be? X plus 3 and x minus 9. And the neat thing is, if I took those factors and distributed them, a lot of you guys use FOIL. If I multiply those together, I will get that polynomial. The polynomial and the roots and the factors are all tied together. And you can create any one from any of the others. All right. For those of you who don't have calculators, pair up with somebody who does. And I do ask that you take turns punching things into the calculator. 16. I'm not going to do 16, but I'll talk about it. What do you notice about 16? Okay, and that's not a problem. That if it equals 0, you're going to have 3 roots. Well, you can have as many as 3. There might only be 1, there might be 2, or there could be 3. And it will have 3, which means it will have 3 factors also. Yeah. 15 could very well be imaginary. I'm not sure. But there are answers on the back, right? I only have, hold on. Yeah, if it doesn't touch the, oh, I see. Yeah. Yeah, the answers start at 19. If it doesn't touch the x-axis, then it has no real roots. It still has roots. They're just imaginary. No real roots. Just list all 3 roots, and then you'll have 3 separate factors. Yeah, you'll have 3 sets of parentheses instead of 2.